Hello everyone, I am Sunish. I am a technical marketing engineer part of HPE. Today I will be presenting the BIER technology together with Human from Nokia and Malaka from Keysight. So what we have done, right, last year we have done the multicast replication support on both the Nokia and HPE nodes. So wherein the Keysight added us the encapsulation on the decapsulation functionality. Basically, the PMSI tunnel got created from the Keysight, and the multicast packet, which got encapsulated with the BIER header, reached both HP and Nokia node. Then it does the replication on those packets and sent to the receiver side. So this year, what we have done, the tunnel creation, both encapsulation as well as the decapsulation, we tested on HP node as well as on the Nokia node. Now we have 3 players here. From HP side, we have a PTX 10002 36QDD, and from Nokia side, it's a 7750 SR1. And Keysight added as the source of the multicast traffic as well as the BIER packet itself. Now, before we dive into the BIER technology, basically the intro part of the testing, right? Let me brief you on what is BIER, right? BIER stands for Bit Indexed Explicit Replication. It is a multicast technology created for the service provider domain, right? So the eventual goal is how best we can reduce the state in the service provider core from P2MB tunnels so that the state information will be carried in the multicast data, right? And there won't be any state kept in the service provider core. So in the BIER, right, we are having 3 different layers of layers we can see. One is the underlay, and the second one is the BIER layer, and third one is the overlay, right? So to understand the BIER one, just consider that you are having a service provider domain with 100 nodes, right? What we will be doing, we will be assigning a unique number to each of the node. That is nothing but the BFR ID, right? That number represents a bit position in a bit string. That means if you have 100 nodes in the service provider network, behind which you are having interested source or multicast listeners, right? You will be assigning a number. That number represents a bit position in a bit string. So if a multicast packet is coming to one of the P node, right, and if each and every node, basically the remaining 19 nodes are now interested in the multicast data, what we will be doing, we will encapsulate our original multicast data with the bit string, and in the bit string, right, we will be setting all bits set to 1, right? So imagine that out of the 100 nodes, right, we are interested only in the odd nodes. Odd nodes are only interested in multicast data. What we'll be doing in the bit string, we will be setting the bit position 1 to the odd numbered BFR nodes, right? So in BIER, right, as I said, there are 3 layers are there. As and when we configure the BFR ID, right, which is a unique number which represents the bit position in the bit string, right? We have to communicate among the nodes in the service provider, right? So how are we doing this one? We'll be using the IGP. We are having support from ISIS as well as OSPF, right, which will carry this information in their databases and circulate it among the nodes in the system. Once the IGP carries and shares the information across the nodes, we'll be having the BIER routing table as well as the corresponding BIER forwarding table in the PFE, right? Now, BIER layer is nothing but the packet is coming. It is encapsulated with a BIER header, right? Now, imagine that in the BIER domain, right, we are having 1024 interested nodes. That means you have to create a BIER header with a 1024 bit set, right? So 1024 means you will be having 128 byte of header encapsulated with the data, right? Now, there is a concept called bit string length. Basically, instead of sending a 1024 bit or 128 byte of header, right, we can split it into 4 chunks. Each chunk is 256 bits. That means instead of 128 byte, we can encapsulate it with a 32 byte of information, right? That is nothing but the set identifier and the subdomain carries in the BIER domain. Now coming to the overlay part, right? So we created this network where we can find out, okay, if multicast packet is coming encapsulated with a BIER header, that header contains the information about interested listeners, right? Now we should have a mechanism to figure it out who are all my interested listeners, right? So that is taken care by the overlay part, right? So our go-to protocol is BGP, right? On the BGP side, we are having the support from MVPN, EVPN, and global IP multicast, right? So those will be taken care with respect to BGP1. Now, on the BIER, right, wherever the encapsulation happens, right, this is nothing but the start of the tunnel. It is the BFIR node, that is BIER forwarding ingress router. And wherever the decapsulation happens, it is the BIER forwarding egress router. Now coming to the topology which we used for 2026 Interop, we have 2 nodes from HP, 2 nodes from Nokia, right? And one of the node from HP acts as a source, basically performs the encapsulation part as well as the decapsulation part. One node from the Nokia performs the same encapsulation as well as decapsulation. So we have encapsulation and decapsulation happening on both Nokia and HP node, and one node from each of us, right, will perform the transit functionality. Now, we have done 3 main test cases, right, for the Interop. The first 2 test cases, we will be performing the encapsulation and the decapsulation, wherein the Keysight performs the source of the multicast data. In the second test cases, what we have done, both HP and Nokia nodes act as a pure transit node, right? And the BIER packet, basically the multicast packet, encapsulated with BIER header, is sent from the Keysight, and the BIER packet will be hitting both Nokia and HP node. And the third test case is basically the HP and Nokia node act as the BFIR node, basically performs the encapsulation part, and the decapsulation part is taken care by the Keysight. So let me move to the demo part. So as you can see here, I have a adjacency, ISI's adjacency, and show ISI's database extensive match BIER. As you can see here, we are using the underlay, nothing but the ISI's protocol. I am carrying the BIER domain. In the BIER technology, we are having 256 domains are supported. What you can consider something like, okay, you are having a service provider network, right? In that service provider network is logically divided into 256 separate domains. Each domain caters for a different quality of experiences or different security perspective, right? And in each of the domain, we can assign a unique BFR ID, right? And what are the different algorithms we are supporting it. So once the IGP is up, right, we will be having the BIER neighborship up and running, right? Now coming to the overlay part, right? Overlay, what we are using the BGP1. So I have the BGP neighborship up and running, right? Now, if you look at the topology diagram, I have a multicast source behind the HP node, right? For that multicast source, there is a receiver behind Nokia. That means the encapsulation happens at the Nokia's HP node, and decapsulation happens at the Nokia node. Similarly, on the Nokia side, right, there is a multicast source behind Nokia for which the decapsulation happens on the HP node. So what I'm going to do here, so show route advertising protocol BGP 10.0.0.35, that is nothing but the Nokia node, right? So you can see here table bgp.mvpn.0 table. Okay, let me show you the other one. We have the ISI's adjacency, show ISI's database match BIER. It contains the BIER information, show ISI's database extensive match BIER. It contains the BIER information, all the subdomains, BFIR IDs, and so on. Then I have show BGP summary, nothing but your overlay part, right? Then show route advertising protocol BGP 10.0.0.35 table bgp.mvpn.0 table. You can see from the HP node, right, I'm advertising 2 routes. On type 1 routes, type 1 routes is nothing but the auto discovery route. So if I am performing that on match prefix 1:* detail, you can see that one, it is the type 1 route carrying the respective route target, right? Now, if you look at the type, if you look at the show pim join extensive, so what will happen, instance VPN, if you see here 230.1.1.1, this source, this is a multicast source behind the HEP node, and this is a multicast source behind the Nokia node, right? So what is here, for the 230.1.1.1, I have a source is here, which is behind the HP node, and I have the downstream interface. Downstream interface is nothing but my MVPN pseudo node, right? So which can be shown as show multicast route extensive instance MVPN A. You can see here, I have a source. This is the source of my multicast. This is my source of the multicast data, right? This is my source of the multicast data, and I am sending the multicast data for this group to 30.1.1.1, and downstream interface is nothing but my BIER header, right? This is how we are performing it. I'm just handing over to Human. He will be showcasing the results on Nokia node. Thank you.
So I think we had a very good detailed technical explanation from my colleague from HPE, but maybe I'll take it a step higher level at 20,000 feet. So I was involved with BIER in IETF from almost day zero, and basically the entire idea behind BIER was to bring source routing to multicast. So basically when it comes to BIER on the transit routers, there is no multicast state. And you might say, okay, what is the point of that? When it comes to other type of technology in multicast, when you have PIM, even MLDP or point-to-multipoint RSVPTE, for every single replication, at every single router, you need to create a state. So what is a state? An incoming interface, replication, and a bunch of outgoing interfaces. This is very heavy on the routers. When it comes to memory, when it comes into the forwarding, it becomes very heavy because multicast uses more memory than unicast. The entire idea behind BIER, and if I go back, I would change the name from BIER to something like segment routing or source routing for multicast. BIER stands for Bit Indexed
Explicit.
Okay, I forgot the rest of it actually.
Explicit replication.
Thank you very much. So it stands for that, but it's really source routing for multicast because there is no state on the transit router. So another thing that we've been seeing in IETF is that because there is no state on the transit router, it is becoming very relevant even in the world of the AI. So if you can imagine in the world of the AI, when you have a large language, when you have an LLM, and you have the server trying to send a bunch of calculation to the bunch of GPUs, the server decides where the packet is supposed to go. It decides that I need to send a packet to GPU 1, 2, 3, or the next packet goes to GPU 5, 6, 7. So now if you can imagine, you need to create, if it's PIM that is being used to send these LLM models to all the GPUs, with PIM you need to create estates, multiple estates. It's like an n to the power of 2 type of issue with PIM. With BIER, as long as that server talks BIER inside their NICs and actually feeds to the NIC that I want to send this packet to GPU 1, 2, 3, it becomes a very simple equation. The server can actually build that BIER header and actually put the payload, whatever it needs to, and it shoots it through the network, and transit routers actually replicate those based on the BIER bed index, and off it goes to the GPUs. So literally, there is no configuration or no signaling on the transit routers. And by the way, there's going to be a prize for somebody that can actually decode this line right here with all the zeros and bits. If you decode that, we can actually give you a prize. This is the BIER header. So every place that you see the 4, that actually stands for a leaf router, or in the case of AI, it actually stands for one of those GPUs. So this node 34 is a transit router. And I'm not going to go too much into the details of what the CLI is doing here. The main point I'm trying to make here is that's the single BIER state that on the transit road, based on these 4 lines, the transit node can actually replicate the packet to 256 or even more of the leaves. So you can see it's a very a small data path configuration, that it consumes a very small data path memory, but that bed string actually says when the packet comes on, for each leaf router, where it should be forwarded. If this was PIM, you would see pages and pages of state information for every single SG throughout the network. So that's the transit router. And now going to the actually leaf router or the PE router, the first thing that you need to understand when it comes to the NG and VPN with BIER is you need to be able to resolve the source of the multicast. And to do that, you actually need in your VPRN, you need to bring up your unicast configuration. So with the unicast configuration, you can actually resolve where the source is. And on top of that, obviously, you need to bring out your next generation NVPN, and you need to say what kind of a provider tunnel you can use in there. Provider tunnel can be MLDP, RSVPTE, 3-seed, or in this case, it is PIM. It is BIER. So after we do that, everything else, the overlay, is exactly like any other NGM VPN. So regardless of whether this is BIER, MLDP, or point-to-multipoint RSVPTE, the overlay is exactly the same. So if I actually show you one of the overlays, so here's the routes that we actually advertised, we received from the Juniper. You can see there are 3 different route types. You can go to the RFC 6514, figure out all the 7 route types that we have for multicast, compared to 1 or 2 that there is for unicast. But as soon as we install these route types, we can understand where the source is, where the leaf is, and the traffic starts flowing over the BIER with the simplified forwarding table. So just to make sure that you guys see that we are not actually faking this, after the NGM VPN layer comes over BGP, and this is BGP v4 peering, and the BIER information are actually advertised through ISIS. We can actually show you so this is the access interface, the UNI interface toward the IXIA, and we can actually show you that the traffic is going. So I think you're sending 1,000 packets, and give or take, so you can see that the traffic is actually going up by 1,000. One more thing I want to put on the picture here is that this demo was actually done between HPE and Nokia, but I do not want to exclude Huawei. They do have this technology as well. And in 2025, we actually brought up the Nokia routers with Huawei, and there was full interop. So basically, when it comes to BIER, Nokia can interop with Huawei, it can interop with HPE, and the technology is mature enough to start deploying in your network. That's all I got. I pass it to my colleague.
So Malek from Keysight here. Let me show you how we model BIER under our traffic and network emulator IX network with Keysight. So I'll be focusing on ISIS underlay and BGP overlay for this. So we'll be starting with ISIS, where we have configured BIER under the ISIS routing level. Here we can configure some parameters like the bit string length, the subdomain ID, and for example the BFIR ID. This will make each node construct their own BIER forwarding table so that the multicast traffic can be forwarded efficiently through the network. Afterwards, we establish a BGP session that will carry our MVPN routes. And the in VPN range, VPN overlay, sorry, where we are going to configure the sender side and the receiver side and the sender side here, so that and can be carried over BGP control plane. Afterwards, we are going to advertise some BGP routes so that our multicast traffic could be through BIER domain. So with this, we can conclude the two PE nodes that were connected to HPE and Nokia. And we have CE side that we used for the first test, where Nokia and HPE were acting as BFIR and BFER, and we just emulated some multicast route sender and receiver. So what we want to test here that afterwards is that once the ISS and the BGP sessions are up and all the protocol are started, we can start our traffic. And under the traffic session, where we can view the result, we can see here our bidirectional traffic has no loss and is been stable and been running from quite some time right now. So with this, we can say that we have both validated the control plane and the data plane for this testing. So in conclusion, we can say that with IX Network, we can emulate end-to-end BIER, I would say, topology from control plane to traffic generation through a multi-vendor, where we did the test this year with Nokia and HPE, and last year with Huawei as well. And this is a huge success for us to do this test. So thank you.